Picture yourself floating, not in a pool, not in some half-remembered dream, but in the deepest, emptiest stretch of space, somewhat out in the void between Earth and Mars. You're sealed inside a small spacecraft. The walls hum. Outside, it's just darkness, and the occasional pinprick of light, impossibly far away. Everything seems fine. The mission is on track, your instruments are green, your oxygen is holding, and honestly, you feel completely normal. But right now, at this exact moment, something invisible is moving through those walls, moving through you. Tiny particles punching straight through the hull, through your skin, your organs, rewriting the genomic integrity of your cells. These are instructions you absolutely need for survival. You can't feel it, you won't hear it, and by the time anything seems wrong, it's likely already been happening for months. This is radiation, not the glowing, obvious kind from old sci-fi films, the real kind, the quiet kind. And it may be the single most underestimated problem standing between us and any serious human future in space. Yet somehow it barely comes up in public conversations about Mars missions, about moon bases, about all those grand plans to become a multi-planetary species. So let's actually talk about it. What radiation is, why Earth has been quietly shielding us from it our entire lives without us noticing, and what it would honestly take to survive a journey beyond this planet. By the time we're done, I think you'll look at the sky a little differently.
The word radiation tends to conjure something specific, a green glow, a nuclear plant, some kind of obvious warning sign. That picture isn't really accurate, at least not for what we're talking about. Radiation at its core is just energy moving through space. Sometimes it's waves, sometimes it's particles, actual physical HZE particles, high Z and energy, flying at extraordinary speeds. The light coming from a lamp in your kitchen is technically radiation. So is the warmth from a fire. The thing that makes space radiation different isn't what it is, it's how much energy it carries. Here's a way to think about it. Imagine someone is firing tiny, invisible projectiles at you from every direction, millions every second. They pass through your clothes, your skin, deep into your body's interior. You feel nothing. But they're not just passing through harmlessly. Some of them hit the machinery inside your cells, the DNA, the long, twisted molecules that carry the biological blueprints for literally everything your body does. And here's where it gets genuinely alarming. Ionizing radiation damage to DNA doesn't work like a bruise or a cut, where your body patches it up and moves on. Sometimes the damage is subtle, a small change here, a broken sequence there. And if the wrong instruction gets scrambled, a cell can start misbehaving, ignoring the normal rules, multiplying when it shouldn't. That's what cancer is, essentially. Cells that have lost access to their biological rulebook. What space radiation appears to do, based on what we've observed so far, is accelerate and amplify that process in ways that don't have clean parallels to anything we experience on Earth.
Here's something I find genuinely strange when I think about it. You have spent your entire life inside one of the most effective radiation shields in the solar system, and you have almost certainly never once thought about it. Earth has a magnetosphere. You probably learned about this as a simple magnetic field. It's what makes compasses work. It's why the northern lights happen. But its more fundamental job, the one that actually matters for life on this planet, is to act as a deflector, a bubble that wraps around Earth and pushes away a huge portion of the solar particle events streaming toward us constantly from the sun. Think of it this way. You've lived your whole life inside a house, and outside there's been a relentless storm. Not rain exactly, but a constant high-energy particle barrage that never ever stops. You've looked out the window and thought, it's a bit gray out, with no real sense of how violent it is beyond the glass. That's the situation. The storm is real. The house has just been very good. The sun, it turns out, is not the serene ball of warmth it appears to be from here. It constantly sheds streams of charged particles, what physicists call the solar wind, radiating outward in all directions, including toward us. Without Earth's magnetosphere intercepting most of it, the surface of this planet would look very different. Life, as far as we can tell, would look very different. The moment you travel far enough from Earth that its magnetic protection no longer reaches you, the full force of that storm hits your spacecraft. Nothing in the way, no buffer. A journey to Mars, which sits roughly 225 million kilometers away at its closest approach, would take somewhere between 6 and 9 months. For nearly the entire trip, you'd be unshielded. That's not a brief exposure. That's an extended stay in an environment that, for most of human history, nobody had to think about surviving in.
When scientists talk about radiation risks in deep space, they're actually describing two fairly distinct threats. They come from different places, behave differently, and present different problems. The first is the sun. Solar particle events, sudden enormous bursts of energy that shoot out without much warning, can hit an unprotected spacecraft with a radiation dose that isn't just uncomfortable, it's life-threatening. There's a related phenomenon called a coronal mass ejection, where the sun essentially hurls a massive cloud of charged plasma into space. If one of those catches your crew mid-journey, the situation becomes critical very quickly. Scientists can sometimes predict these events a little in advance, but a little is doing a lot of work in that sentence. You might get hours of warning, you might get less. The second threat is arguably worse to deal with, and it doesn't come from the sun at all. It's called Galactic Cosmic Radiation, or GCR, and it comes from everywhere else. Distant supernovae, collapsing stars, energetic events at the far edges of the galaxy. These particles have been traveling through space for an incomprehensibly long time, and by the time they reach your spacecraft, some of them carry extraordinary amounts of energy. We're talking about individual HZE particles that hit with more force than you'd expect from something you can't even see. The brutal difference between the two threats: solar radiation has some pattern, some warning, some source you can watch. Galactic cosmic radiation arrives from all directions at all times without any signal in advance. There's no dodge here. There's no safe angle to turn the ship. It simply exists constantly in every direction you could possibly point. For a crew on the way to Mars, both of these threats are present simultaneously for months on end. Neither one takes a day off.
So, what does prolonged radiation exposure actually do to a person? The honest answer is several things, and researchers are still working out the full picture. Cancer is the most widely cited risk, and for good reason. When enough DNA damage accumulates in enough cells, the probability of something going wrong in a serious way goes up significantly. It's not a certainty. Bodies have repair mechanisms, and most individual hits get corrected, but the more radiation you absorb, the more you're testing those repair systems. Astronauts on the International Space Station, who are still partially inside Earth's magnetosphere, already show elevated cancer risk compared to the general population. A Mars mission would involve substantially more exposure for substantially longer. But it's not just cancer. Some astronauts have come back from extended ISS missions with measurable changes to their vision, a specific kind of structural change to the eye, now recognized as SANS, spaceflight-associated neuroocular syndrome. There's also growing evidence that radiation in deep space may affect the central nervous system in ways that go beyond traditional radiation sickness. Studies on rodents exposed to simulated GCRs have suggested possible cognitive effects, problems with memory, attention, spatial reasoning. Whether those findings translate directly to humans is still genuinely uncertain. What makes all of this particularly difficult is that the damage doesn't work like a single bad event you recover from. It accumulates. Every day of exposure adds to the total. The analogy I find most useful isn't being hit by a car. It's more like being slowly, continuously worn down by friction you can barely detect. By the time you notice the wear, the damage is already done. The most obvious solution sounds straightforward. Just build a thicker ship. Line the walls with passive mass shielding and absorb the radiation before it reaches the crew. For solar radiation, this approach has some merit. Aluminum has been used as basic shielding, and it helps. Water turns out to be surprisingly good at absorbing certain types of particles. Some designers have proposed building water tanks into the walls of spacecraft specifically for this purpose. Galactic cosmic radiation is a different story. These particles carry so much energy that most materials don't meaningfully slow them down. And here's the infuriating part. Heavy shielding can sometimes make things worse, because when those high-energy particles hit dense material, they can produce secondary radiation, a kind of particle spray that wasn't there before.
You can't just keep adding mass. And even if you could, the weight required to fully block GCRs would make the spacecraft physically impossible to launch with any technology we currently have. One idea that keeps coming up is building an active magnetic shielding system around the spacecraft, essentially a small-scale version of what Earth does naturally. In principle, it's elegant. In practice, generating a magnetic field strong enough and stable enough to actually protect a crew using hardware that fits on a spacecraft is far beyond what engineers can currently build. It's an active research area, not an available solution. There's also pharmaceutical research, the idea that drugs might help cells repair radiation damage faster or protect their genomic integrity in the first place. Some early results look genuinely promising, but promising in early trials and ready to protect a crew of 6 for 8 months in deep space are very different things. The honest state of things is this: we have partial mitigations, we have active research directions, and we have some genuine uncertainty about which approaches will prove most effective. We do not have a solved problem.
Carl Sagan's pale blue dot, that image of Earth as a speck of dust in a sunbeam, tends to make people feel small in a philosophical sense. I think it has a more practical meaning too, one that's easy to miss. That dot is, as far as we know, a genuinely unusual place. Billions of years of planetary physics have conspired to produce a magnetosphere, an atmosphere, and a position in the solar system that together create conditions where complex life doesn't immediately get irradiated into oblivion. We didn't choose this, we didn't build it, we just woke up inside it and took it entirely for granted. The universe, in contrast, isn't hostile so much as indifferent. The radiation isn't targeting us. There's no malice in a galactic cosmic ray. It's simply what space is, a high-energy environment that has no particular interest in preserving the molecular structures that make up a human being. Earth is an anomaly, the quiet, shielded exception to an otherwise relentless background. Getting to Mars isn't just a logistics problem. At some level, it's about whether we can engineer an answer to a billion-year-old question: what happens to life when the shield runs out? We don't have a complete answer yet, and I think we'd be better served, as a culture, if we acknowledge that honestly, rather than treating it as a detail to sort out later. The universe has been pretty clear that it won't be making exceptions.